All right, let's talk about something that's the secret sauce of any AI project, but it's the part nobody ever really sees. We're talking about data preparation. This is the bedrock, the foundation that decides if an AI model is going to fly or if it's going to fail spectacularly. This is the stuff that really makes or breaks modern AI. So let's just kick things off with a question. What do you think would happen if you just ignored all this prep work? If you just took a bunch of raw, messy, unfiltered data and threw it at a super smart algorithm?
Well, it's pretty simple, really. You'd be setting yourself up for a total disaster. It's exactly like trying to build a giant skyscraper on top of a swamp. Sure, it might stand up for a second, but it has no foundation. It's unstable, and eventually, it's all coming down. It's the exact same with AI. Garbage in, garbage out. A flawed foundation will always lead to a flawed model, no matter how fancy your algorithm is. So, if we're going to build that solid foundation, we have to know what we're building with, right? You got to understand your materials. And in the world of machine learning, your materials are your data. Generally speaking, data comes in two main flavors. First, you've got structured data. You know this stuff. It's your classic Excel spreadsheet or a database. Everything is organized in neat rows and columns, all tidy and easy for a computer to read. Then you have unstructured data, and that's, well, pretty much everything else in the world. We're talking text from emails, images, audio files, videos. It's all the messy, chaotic, real-world stuff that holds a ton of value but doesn't just slot neatly into a table. And to give you an idea of just how massive this unstructured world is, take a look at this. This is just a tiny glimpse of the ImageNet dataset. That's over 14 million images, every single one of them labeled by a human. This is the kind of stuff that's been used to train some of the most powerful computer vision AIs we have. Each photo is one piece of unstructured data. The scale is just mind-boggling. And of course, it's not always black and white. There's also this middle ground, semi-structured data. So it's not a perfect, rigid table, but it isn't total chaos either. It uses things like tags or markers. If you've ever seen an XML or a JSON file, that's what we're talking about, to give the data some kind of organization. It's a really flexible hybrid of the two.
Okay, so now you know what kind of data you're dealing with. And this is where the real work begins. Welcome to what I like to call the Great Data Cleanup. This is where we roll up our sleeves and turn that messy, raw information into something we can actually rely on. So the first thing you're going to run into almost every single time is missing information, gaps in your data. You've got a spreadsheet with some empty cells, maybe someone skipped a question on a form, or a sensor just glitched out and didn't record a reading. What do you do with those empty spots?
Well, you've got a few options, but each one's a trade-off. The easiest thing to do is just deletion. If a row's missing a value, you just get rid of the whole row. But here's the catch. You're also throwing away all the other information in that row, which isn't great. If you can't afford to lose it, you can try imputation. That's a fancy word for filling in the blank with a good guess, like the average value for that whole column. Or you could use a more advanced model like a decision tree that's actually smart enough to just work around the missing pieces on its own.
All right, what's next on our cleanup list? Oh yeah, another classic headache, duplicates. The exact same information entered into your system twice, or maybe 3 times, or more. These accidental copies can really mess things up.
Now, on the surface, the solution sounds super easy, right? Just find them and delete them. But it can get tricky, because sometimes the duplicates aren't perfect copies. Maybe there's a small typo or different formatting. If you don't catch these, your model might start to think that piece of information is way more important than it actually is, and that will totally bias your results. It's a simple concept, but getting it right is absolutely essential.
And finally, the last big cleanup task is tackling something we call noise. And it's pretty much what it sounds like. It's just random static and junk in your data. It could be a simple typo, a sensor that glitches and reports a crazy number, or a data entry error that says someone is 200 years old. All these little random errors can seriously throw off your model. So how do we filter out all that static? Well, we've got a couple of tools. One way is to go hunting for outliers, those really extreme, bizarre values, and just remove them if they're obviously an error. You can also apply different filtering techniques that help smooth out the data. Or, just like with missing values, you can pick a specific type of model that's known to be more robust, meaning it's just naturally less sensitive to this kind of noise and can kind of ignore it. Whew. Okay, our data is squeaky clean. We're done, right? Not quite. Just because it's clean doesn't mean it's ready for a machine learning model. Now we have to actually shape it, transform it into a language that an algorithm can speak.
First up, let's talk numbers. Imagine you've got data about people, and you have two columns, their age, which might be between, say, 0 and 100, and their annual income, which could be in the hundreds of thousands. An algorithm, by default, will think the income number is way more important, just because it's a bigger number. We need to fix that. We need to put them on the same scale, on a level playing field. There are two really common ways to do this. Over on the left, we have normalization. This basically squishes all your values into a tiny range, always between 0 and 1. Then on the right, you have standardization. This is a bit different. It transforms the data so that its average becomes 0 and its standard deviation becomes 1. Both of these are fantastic techniques to stop one feature from dominating the others just because its numbers happen to be bigger. Okay, so the numbers are handled. But what about all the other stuff? You know, the data that's just words? How does a machine make sense of categories like red, green, and blue, or cat and dog? This is where a really clever trick called one-hot encoding comes in. It sounds way more complicated than it is. Let's say you have a color column. What this process does is create a brand new column for every single possible color. So suddenly you have new columns called is_red, is_green, and so on. Then, if the original entry was red, it just puts a 1 in the is_red column and a 0 in all the others. It's a brilliantly simple and effective way to turn categories into numbers a machine can crunch. All right, we are so close. We have cleaned our data. We have transformed our data. There is just one last and maybe the most crucial step of them all. We have to split it. Now, this is absolutely critical. After all that hard work making your data perfect, you can't actually use all of it to train your model. I know, it sounds crazy, right? But think of it like this. It's like you're studying for a big exam. You wouldn't study by just memorizing the answers to the practice test, because then you'd have no idea if you could solve new problems. You have to save some questions for the real test to see if you actually learned anything. And this is exactly how it's done. You take your beautiful, complete data set and you slice it into two pieces. The bigger chunk becomes your train set. That's what you use to actually teach the model. The smaller piece, the test set, you lock away in a vault. You don't touch it until the very end. That's your final exam to see how well the model performs on data it's never ever seen before. So what's the magic ratio? Well, a super common rule of thumb is an 80-20 split. You use a big chunk, 80% of your data, for training. You want to give the model as many examples as possible to learn from. And then you save that precious final 20% for a truly fair and honest test. So, after going through all of this, what's the one big thing you should remember? It's this: having high-quality, clean, well-prepared data is almost always more important than having the most complicated, fancy algorithm on the planet. The old saying is absolutely true here: garbage in, garbage out. The quality of that foundation really is everything. And that leaves us with a final, kind of mind-blowing thought. Our world is literally swimming in messy, unstructured data everywhere. Social media posts, satellite images, medical scans, you name it. So the real question is, what incredible discoveries, what amazing potential is just sitting there, waiting to be unlocked, if we just take the time to prepare that data the right way?